Okay, so I'm going to talk about a paper that came out a month or two ago, a third in a series with Malcolm Perry and Stephen Hawking, and we've been joined by Sasha Heiko in this most recent one. And the starting point of this longer project is some recent insights into the structure of very long wavelength soft modes or pure diffeomorphisms in quantum gravity and gauge theory. And let me just say a few things about them. One is that they have a very rich structure, which is in general governed by infinite dimensional symmetry groups. The earliest example being BMS, but there are more, and we don't, well, the second thing I want to say, well, we don't understand, many things about them that we don't understand. We know that they're important, especially at the boundaries of space-time, which includes null infinity, but also if we have a horizon, they can become important there. And the third thing I want to say is that these are really still not well understood. Even the case of null infinity, there's a rather tortured history of different proposals and counter-proposals, right and wrong things. Still, today, we don't know what the group of soft modes or non-trivial symmetry is that acts at null infinity. And I would remind you that in all the spectacular progress that we've made in ADS-CFT, the starting point was identifying what the symmetries were, and we're not even there yet for flat space, though I don't want to sound discouraging because I think it's a problem which there is an algorithmic way to understand, and we will be able to fully understand it. In this talk, that's of course an important problem, but not what I'm going to talk about. I'm going to talk about an even harder problem, which is understanding the boundary of space-time that occurs at the horizon of a black hole. And why should we expect this is particularly interesting? Well, one of the things that we don't understand about black holes, I don't need to say in this room, is we don't understand where the information goes, how it comes in and out, and how it's stored, and so on. But soft modes are a cheap way to store lots of information. And so they're certainly a prime suspect in any kind of analysis that we would like to do of what happens to black hole information. And moreover, one of the things that we've learned is that, related to over here, that there are an infinite number of conservation laws in asymptotically flat space, which imply that there are constraints that they impose on the states imply that there must be correlations between hard and soft modes, because there are both hard and soft terms in the conservation law, and that is the basic motivation for thinking that this is an interesting thing to think about. Now, what do we do? What do we do in this third paper? Well, in this third paper, we do try to address what it might have to do with the information paradox, and in particular, how black holes, real-world black holes, might store the Bekenstein-Hawking's worth of information. And in the process, we try to bring the work that we've done in the previous papers closer to the kind of analyses that have been successful in string theory, because after all, in string theory, the crux of understanding where the entropy comes from had to do with understanding diffeomorphisms which act non-trivially on a black hole, and that is the same kind of thing we're studying using rather different tools in our more recent enterprise. And so let me give a review of what an outline of what I'm going to talk about. I'm going to talk about, I'm going to review some work from 2010 on so-called hidden conformal symmetry. And that work was really kind of a some numerology, but using some of the more recent insights, we've been able to take that a step or two, not all the way to a derivation, but we've been able to make it a step or a little bit more plausible than it was. And so we're going towards, but have not arrived at, a derivation. We've filled in some steps. And finally, in thinking about all this, since this is a talk about quantum entanglement and so on, I'm going to make some speculative comments at the end about the relationship between the entanglement. This way of looking at things leads one to think about the relationship between the Hilbert space inside the black hole and the external Hilbert space. Speculate on the entanglement of the exterior and interior Hilbert space. And these won't really be new speculations, but I'll be saying them a little bit differently than how they've been said before. Okay, so in string theory, when we first computed black hole entropy in string theory, it seemed like it was something which was very, very specific to string theory, having to do with the properties of d-branes and all the property factors of 2 and pi and all that to get the quarter to work out exactly right. But later on, we realized that the analysis we did didn't really depend on the details of string theory, that it was guaranteed to work, and that it really followed from some rather plausible assumptions, like a good ultraviolet completion, a unitary Hilbert space, and so on and so forth, that any black hole with a near horizon ADS region and any consistent kind of quantum theory of gravity, one could argue, just using the properties of the Einstein equation, that for any consistent ultraviolet completion, there would have to be a consistent accounting, including the 1/4 of the microstates of the black hole. Now, more recently, what Hawking and Perry and Heiko and I have been doing is analyzing the properties of diffeomorphisms which act non-trivially on the horizon of a black hole. And our starting point were the ones that were understood the best, the super translations. It's understood the best how they talk at infinity. But from the outset, it was clear that the super translations were not rich enough to lead us to an understanding of everything that might be inside a black hole. And so we types of diffeomorphisms which might act non-trivially on the horizon of the black hole. Now, let me just say a word about this. So what is done in string theory, if you have a black hole with, let me not commit myself to what the singularity looks like inside here, but this is the horizon of the black hole. Usually we take a region, a little band, which goes very near the horizon like this. And in the ADS black hole, we divide the space-time along this line, along the outer boundary of the near horizon ADS region. And then we use ADSology to count the states of everything that's inside here. That's I've gone for 15 minutes, or I have 15 minutes left?
15 minutes plus 10 questions.
Okay. All right. So but the scale invariance tells you can push that. There's no preferred place to put this boundary. It's just a line that you draw in space. And in fact, it better not matter where you put the boundary. And if you wish, you can push it arbitrarily close, or in fact, you can push it to the horizon, and you can set up the calculation in such a way that you can think of this as the counting as counting the microstates of the black hole itself, rather than the microstates of ADS. Okay, now okay, so now let me start with, all right, let me say first of all, the problem of understanding all the diffeomorphisms which act non-trivially on the horizon of the black hole is a very hard problem. We're not going to try to solve that. The analogous problem has not been solved at null infinity. It was proclaimed solved falsely many times. Errors were found in the argument. It's a very subtle argument. We'd like to do that, but it's hard. We haven't. So what we've done instead is just to try to find some diffeomorphisms that appear to act non-trivially and see if they're interesting ones. And indeed, there are some very interesting ones that we've constructed inspired by earlier work. And they're the so-called hidden conformal symmetries, which act on a region near a generic Kerr black hole in the region of phase space. So it's a region of phase space where if you take a scalar field and you scatter it off a black hole, and if omega is the frequency of the scalar field times the distance from the black hole is less than 1. That's not a region of space-time. That's a region of space, phase space. And in this region, I think I'm not going to write it all off because somehow time is really zooming here. In this region, you find that there's an emergent conformal symmetry. And there's two ways of seeing this. The first is that the solutions in the near region of the wave equation are hypergeometric functions, and hypergeometric functions are representations of SL2R. And another way to see it is to look at the scattering amplitude of a massive scalar off a black hole in this region, and they take exactly the form of a two-dimensional conformal field theory, where, let me just write one term, P absorption, has a term in it which looks like gamma of H left plus I omega left over T left. And there's a similar right factor, which everybody who studies conformal field theory knows looks like a scattering amplitude in a conformal field theory So h left here will be the angular momentum L of the scalar field, and omega left is 2m squared over a omega, and t left is r plus minus r minus over a. And similarly for scalar, h right will be equal to L, omega right will be equal to 2m squared over a omega minus the angular momentum m of the scalar. And if we take the Frolov-Thorne density matrix, which describes the state of an ordinary scalar field, you find that e to the minus the energy over t Hawking minus, where a here is j over m, the energy over t Hawking minus omega m over t, this is the angular momentum of the particle over t Hawking, that just becomes equal to e to the minus omega left over t left minus omega right over t right. So the gist here is that if you just look at the formulas for black hole thermodynamics, it jumps out at you, as many people have noticed. T right is r plus plus r minus over a. That t left and t right are somehow natural temperatures. They're the poles in the wave, where the poles appear in the wave equation. And omega left and omega right are their thermodynamically conjugate quantities. So all of this suggests the hypothesis that a generic Kerr black hole is described by a conformal field theory in which at temperature T left and T right, and then if you make the additional assumption that C left is equal to C right is equal to 12J, number one, and then you make the second assumption that we can use the Carty formula so that the microscopic entropy is equal to pi squared over 3 C left, T left, plus C right, T right, that this just gives exactly the area over 4. This is numerology. But it's impressive numerology, I thought. And moreover, it works when you do Kerr-Newman, it works in higher dimensions, and so on. So that's how far we went 2010. I don't think I ever gave a talk on it around that period, but it sort of hung with me. And what have we done? How many minutes do I have? Wait, I had 10 minutes ago.
I stopped time. I made time real quickly and I stopped it. I apologize.
Are you going to stop it again?
You're done. You just said ignore me. Go ahead.
You just okay. I was like, okay, so okay, so well, you sped me up. It's probably good. Okay, so so now if you go to Boyer-Lindquist coordinates, which you know, they start out as 1 minus 2m over rho squared, where rho squared is equal to r squared plus a squared cos squared theta, and minus 4am r over sine squared theta d phi dt. I'm not going to write the whole thing out, plus dot, dot, dot. There's a very interesting coordinate transformation. W plus is equal to the square root of r. W plus is equal to the square root of r minus over r plus over r minus e to the 2 pi t right phi. W minus is equal to square root of r minus r plus over r minus e to the 2 pi t left phi. And then y is equal to a similar expression. You find, so these are coordinate transformations which make each leaf of fixed theta in a four-dimensional Kerr black hole look like BTZ. Dan?
That's not a question. I'm not raising my hand.
What?
I was just visualizing the coordinates.
You were just playing with your hands. Okay, good. All right, so you take the periodic identification in phi tells that W plus is equal to e to the 4 pi squared t right W plus. This is phi goes to phi plus 2 pi. And W minus is equal to e to the 4 pi squared t left phi, W minus. And y is also identified. And it looks like, just like the quotient that takes you from the Poincare coordinates of ADS to BTZ. We all know that BTZ is a quotient of Poincare coordinates in ADS. And these temperatures that appear here tells you that in the dual field theory, that is turning you the vacuum state into, it's like if you do transformations on the Rindler wedge, you turn the vacuum state into a finite temperature ensemble. So a lot of what we did in the following was just kind of mimicking what you do in BTZ in following our nose and doing a asymptotic symmetry type analysis or a near the horizon type analysis in the covariant phase space formalism for the full Kerr black hole. And the first thing we did was to simply find a set of vector fields on Kerr which have omega left and omega right as their zero modes, but generate two commuting Virasoro algebras. And those vector fields were simply zeta n is equal to epsilon n of W plus D plus, or maybe I should call it zeta plus n, plus 1/2 d plus epsilon n y dy, which may look very familiar to those of you who have studied the Virasoro vector fields in BTZ, where epsilon n is equal to 2 pi t right W plus to the 1 plus I n over 2 pi t right. And we find that zeta plus m was zeta minus n is equal to obeys the centerless Virasoro algebra n minus m zeta n plus m. And this I may look a little funny, but exactly the same thing happens when you do the quotient of ADS3 to get BTZ. You have e to the in phi, and since W plus is the log of, it's the exponential of phi, you would expect such things. So these vector fields are single valued on Kerr. Now, moreover, the zeta 0 is what I've called W right, and there's a second copy, zeta minus n, whose zero mode is W left. And which commutes with this one. And you get it just by replacing the W pluses with W minuses. Okay, so now this was a rather easy exercise. We've just constructed two commuting copies of centerless Virasoro algebra on the Kerr geometry. And these map the horizon to themselves, are divergence-free, and mapped every leaf of fixed theta to itself.
Are they smooth at the poles?
Yes, I think they are smooth at the poles. Okay, now we use the covariant phase space formalism. So the covariant phase space formalism has a long history. I don't think I'll even write all the names, but it was Krinkovich and Witten, Zuckerman, Brown and York, Iyer and Wald, Lee and Wold, Barnick, Flanagan just wrote a beautiful paper on it for the purpose of horizons. And the idea was to construct covariant charges that generated, that were surface terms that generated the diffeomorphisms. And so there's something called the Iyer-Wald charge, which lives on the linearized phase space. So it depends on the diffeomorphism being generated. It's a general formula for any diffeomorphism. It depends on the linearized fluctuation about any background metric. And it depends on the background metric G. And it's equal to 1 over 16 pi. So if we have a surface sigma with a boundary d sigma, which in this case we're interested in being the horizon, you'll have an integral over the horizon of the star of some two-form f, where f can be found in all these papers. F is basically the covariant symplectic form on phase space, which is a two-form, with one of the legs of the two-form replaced by the diffeomorphism that you're interested in generating. So formally, these Q's generate the symmetries. But I want to emphasize formally because they generate it via Dirac brackets, and to actually construct the Dirac brackets, which is almost never done in a concrete way, you have to worry a lot about boundary conditions and zero modes and so on and so forth. And in every real applications, those have played an important role. So F, the Iyer-Wald two-form F, is things like D, its AB components are something like dA HBC zeta C, anti-symmetrized, plus more terms, all of which are linear in the fluctuation H and linear in the diffeomorphism zeta. Now, what Wald and Zupitz emphasized was that this Iyer-Wald two-form was ambiguous up to the addition of what's sometimes called the Wald-Zupitz counterterm, So if you construct this, you're not guaranteed that by the time you get to the Dirac brackets, you're not guaranteed that this thing is integrable. This is just the linearized charge. And by the time you get to the Dirac brackets, you may get in trouble. And you may need to add this counter term. And they figure out what it is in various examples. But it's basically 1 over 16 pi integral over the same thing, d zeta, zeta wedge, some arbitrary function of h, which we call x. These are both one forms. And we found that there was indeed an obstruction in general to the Iyer-Wald 2 form generating these diffeomorphism. And we needed x to be what is sort of the simplest thing you could imagine in this context, which is 2 dxa HAB, so it's linear in H, contracted with what's called the Hagacek 1 form, which is basically the velocity of each point along the horizon. You can find explicit formulas for it in our paper or in the literature. And with an appropriate coefficient, you then can compute the central term by taking the variation with respect to a second zeta of the Iyer-Wald 2 form plus the counter term, and we indeed found that C right equals C left equals 12J. And so then using the Carty formula, as I wrote over here, we got the microscopic entropy. Assuming the Carty formula, we got that the microscopic entropy was equal to pi squared over 3. That's the Carty formula, C left, T left, plus C right, T right, is equal to the area over 4. And we didn't prove that this counter term was unique. Do I have 5 minutes still? OK. Now, in my closing 5 minutes, I want to make some comments which have been made before, but maybe from a slightly different point of view. And they're really in the spirit, if not the letter, of black hole complementarity. So let's go back to this picture here. And I want to think of the dividing line between the interior of the black hole and the exterior. So here's the exterior, and here's the interior, as being the horizon, though it doesn't really make that much difference whether you make it the horizon, the stretched horizon, or the outer boundary of the ADS region. And if we were considering this as a background on which we were, let me use this again. If we were considering this as a background in which we were quantizing a free scalar field theory, then we would say that the full Hilbert space of the free scalar field theory was roughly the tensor product of the exterior Hilbert space with the interior or black hole Hilbert space. And that a state in the full Hilbert space could be written as a linear combination, AB, of sums of states in the interior and the exterior Hilbert space. On the other hand, here we have these charges let's consider a diffeomorphism which has the property that it's equal to either this Virasoro transformation, or for the purposes of this discussion, I could be talking about the stringy black holes, which we understand very well, and I could take my dividing surface to be the exterior of the ADS region. So I want to take it something which is a diffeomorphism which is equal to one of these Virasoro guys in here, and then I just want to multiply it by 0 so that it's 0 out here. And then I can construct the charge here, which depends only on the boundary value of zeta. And so I'll have Q of zeta n is equal to 0. So if I'm trying to do quantum gravity now, and I act on this, the full quantum gravity state, not just a free scalar field, if I act on this with this Virasoro transformation, Q of zeta n, that's equal to, I can write that as a bulk integral, AB, sum over AB, of Q exterior CAB, Q exterior psi A times psi B plus sum over AB CAB psi A Q interior psi B. So that says that this state has to be the combined state has to be a Virasoro singlet. In other words, if I divide it into a state outside here and inside here, it has to be a Virasoro singlet. Now, in the generic case where there's no supersymmetry or anything, every state will be labeled by a highest weight and an element in the representation, and will be uniquely determined by its place in the representation. And so once you know the interior state, in order to make a singlet, you also have to know the exterior state. Or put the other way, if you know the exterior state, how it transforms under this Virasoro, you know the interior state. So that says that the black hole Hilbert space is equal to the exterior Hilbert space. You can learn everything about the exterior state, about the black hole state, by making a measurement outside the black hole. And so this is a different way, which is the spirit of black hole complementarity. So this is a different way of arguing from this kind of group theory that the black hole the black hole Hilbert space is redundant. It can't have independent degrees of freedom. Now, you might wonder how this works in supersymmetric theory, where there is all kinds of degeneracies. And then there could be, as was actually conjectured decades ago, there could be discrete symmetries which are common, ubiquitous in string theory, that distinguish them. But that's another project. So let me stop there, and thank you for listening.